everybody. This is Professor Monty. We are going into chapter 3, which is applied calculus. So we're going to start applying all the rules we learned in the first two chapters. All right, so 3.1, as you can see, it's using first derivatives to classify maximum and minimum values in sketch graphs. First of all, let's talk about when a function is increasing or decreasing. So essentially, a function's increasing if it's going up from left to right. So this function would be increasing. And again, that just means it's going up. And we always read the graphs left to right. Now, formally, what we could do is we could say if x1 is less than x2, then f of x1 has to be less than f of x2. And essentially all that's saying is if I have my x and y axes here, and this is the graph of f, here's x1, here's x2. So we see x1 is less than x2. Well, f of x1, which is the y value, is less than f of x2. So that's all that's saying. I've got an increasing graph. So as I go left to right, the y values are getting higher and higher. And similarly, we can go the other way. If the graph's going down, obviously it's decreasing. So let's just sketch that real quickly. So if I've got a graph and it's coming down this way, well, that graph's clearly decreasing. And again, that just means it's going down. Again, reading left to right. Okay, so we've got that idea, but let me go back and show something on this graph. So if I go up here, this graph that was increasing, notice something about it. Anywhere along the graph, say I've got this point right here. If I look at the tangent line there, notice the tangent line is going up. So in this case, f prime of x is going to be greater than 0, because since the tangent line is going up, the slope is positive. But that's going to be the case any place along this graph. Oops. I like to just say positive rather than greater than 0. Then we have to interpret, oh, greater than 0, what does that mean? Obviously not hard to interpret, but I'm going to say, I'm going to put a plus anytime that we have a positive derivative, just meaning it's going up. Similarly, down here, if I take any point here, left to right, the tangent line is going down. So f prime of x is less than 0, or of course negative. And that would be any place along this graph. It's not a very straight tangent line, is it? And we're going to use that fact that if the derivative is positive, we know the graph's increasing. If the derivative is negative, we know the graph's decreasing. All right, so let's take those ideas and let's look at this graph that I copied down from the problem set. It's problem 4, as you can see. There's a couple things I want to point out here. First of all, we can see when the graph's going up or down. This graph starts to go up and then it starts to come down. Don't look at that arrow. Don't look at the arrow here that makes it, don't think that's going down because we read it left to right. So left to right, we see that's going up. The derivative is positive because the graph's going up. Similarly over here, the derivative is negative. But that's not really what I'm looking at right now. Here's a couple things I'm going to look at. So let's go ahead and erase that. Here's what I want to point out about this graph. We are looking for some different things this time. We're looking for when the function has what they call a relative maximum or a relative minimum. And so let's just list this out real quickly. A relative maximum, and just in layman's term, is highest point in some interval. And so, for instance, right there, we have a relative maximum. Right there, we also have a relative maximum. We'll say rel max, abbreviate it that way. Similarly, relative minimum, oops, that doesn't look great. The relative minimum is the lowest point in some interval. And so notice it doesn't have to be the lowest point in the entire graph, but just in some interval. So if I take, for instance, let's take another color. Well, that point right there, that's going to be the relative minimum. And it's not the lowest point on the graph. We see off to the left and off to the right, there's points lower on the graph of each of those. So it's not the minimum of the whole graph, but it is the lowest point in that interval that it's in. So that little green circle that I drew, it's the lowest point in that circle. Okay, so that's the idea of a relative maximum or a relative minimum. But what I want to point out is if we want to try to find these, note a relative maximum or minimum, we'll abbreviate these. A lot of times they just call them extremum or extreme points. We'll call it extrema, that's plural. A relative max or min can only occur when the derivative, well, let's look at these. Notice this place off to the right. Let me erase those circles. If I look right here where this relative maximum was, and I look at the tangent line's horizontal. Well, if the tangent line's horizontal, the slope of it, or the derivative, is 0. So where the derivative is 0, but also notice this over here, that was relative max also, but the derivative's not 0 there. Remember, the derivative comes from the two-sided limit, and this doesn't have a two-sided limit. From the left, it's going up. From the right, it's going down. There's no point where it's curved like the one on the right was, where we could have a derivative of 0. So at that point, remember the derivative's undefined. So either the derivative is 0 or undefined. And in fact, we have a term for this. And what we call these are called critical values. I'll squeeze that in here so I can underline it. So a critical value, every derivative is 0 or undefined. If the derivative is 0 or undefined, we call those critical values. And those are important because, again, those are the only place that you can have a relative extreme point, a relative maximum, or a relative minimum. Okay, so we're going to go on from there. We've got that nice graph. This title of this chapter, remember, was using first derivatives to classify maximum and minimum values in sketch graphs. What I want to show you how to do is how to sketch some of these graphs. Once we go calculus, I'm not going to sketch each one individually, but I'll show you how to use the calculus to sketch the graphs first. And so we'll do that on a couple of these problems, and then we'll actually go start doing some calculus to find critical values and find the relative extreme points. Okay, so let me jump into my files real quickly. Let's pull up this problem. So let's see, we'll copy this, and then we'll go post it back in here. Okay, so let's see. It says f of x has a negative derivative over negative infinity to 1 and a positive derivative over 1 to infinity. We need to figure out, what does it mean to have a negative derivative? Well, remember, the derivative is the slope of the tangent line. If it's negative, the slope is negative. That means the graph's going down. So notice negative derivative right here, that means it's decreasing. The function is going down from left to right. And then over here where it says it's got a positive derivative, I know the function's increasing. And so now when I go to draw this graph, so we'll draw a grid here. Let's see, it's at 1 where things start to change. And it doesn't matter how high or low we draw this graph. We just know that once we get to x equals 1, notice when it talks about the interval, those are x values. When it gets to x equals 1, it stops going down and starts going up. And that's all we know. I don't know if it's above the x-axis, below the x-axis. It doesn't matter. For instance, here's a graph that would work. So say I draw a point right here. And again, that's just an arbitrary point. But I know the graph's coming down till I get here, and then it starts to go up. So it might look like a nice little parabola. Might not. Let's see what else it could do. That graph works. Another idea would be maybe it looks like an upside down, or not an upside down, maybe it looks like a V. That graph is decreasing till we get to x equals 1 and then increasing. The difference in the two, the first one I drew, the parabola, has a derivative of 0 at x equals 1. This one has a derivative that's undefined at x equals 1 because, again, there's no two-sided limit there. But again, I drew the graph that way, but maybe the graph didn't look, maybe it was down here. I don't know. We don't know how high or low it is, but there's a graph that works. So this point right here would be 1 comma something. It doesn't matter. I don't know. Maybe it's -4. We know it's negative if it's down there below the x-axis. But that's a graph that would work. It satisfied those requirements. So there's a variety of graphs that work. And if you look in the back of the book, it's going to say answers may vary. I'm not a big fan of that. I wish they would say, here's one possible answer, but they don't. So that's not terribly helpful. All right, I've got another one of these to look at now that we have the idea. It's going to be more complicated. So let's pull out this other problem and we'll go ahead and graph this. Let's see, so we'll copy that and we'll paste that in here. Let's lift this up a little bit, get that out of the way, and I'll paste it right here. Okay, the graph g of x has a positive derivative over -infinity to 3. So let's kind of sketch what's happening. Positive derivative, what does that mean? It means the graph's going up and from 0 to 3. Remember, now that's not the point 0, 3. That's not an x and y. Those are two x values. From x equals 0 till x equals 3, the graph's going up, is what that means. And a negative derivative over -3 to 0 and 3 to infinity. So it's going down in each of those. The derivative is equal to 0 at x equals -3. That means it has a nice rounded value. The tangent line, well, I'll leave that horizontal line there. That's what the tangent line is going to look like. So it's got a derivative equal to 0 at x equals -3 and at x equals +3. But g prime of 0 does not exist. So at g prime of 0, it's either a corner or maybe there's a hole there. They didn't tell us that this was a continuous function, so it might be a hole. I'm just going to draw it as a corner or a cusp, they often call that. All right, so let's try to draw this graph. And again, answers may vary. So let's see. Something's happening at -3, something's happening at 0, and something's happening at +3. So let's see. Again, I don't know how low I'm starting on the graph, but let's say maybe I'm down here and the graph's going up until I get to -3. Now at -3, it's got a derivative equal to 0, so I better not have a straight line there. So let's make it curved, because then once I get from -3 to 0, the graph's negative, so it's going down. The derivative's negative. So let's say maybe it goes here, and I'll put a point here. So the graph is increasing till I get there. Then it's got a derivative of 0, so it's a nice rounded, there's a little vertex looking thing. G prime of 0 does not exist, so maybe when it comes down here, it's at a corner. So we'll draw it this way and have it go up. So it wasn't nice and rounded like it was at -3, but 0 to 3, it's going up again. And then 3 to infinity, it's going down again. So maybe it goes up this way and maybe it rounds nicely. That's a little too early. Wonder how much of this is going to erase. Oh, good. So let's see, we'll put the dot right here so I see it. So it's going up. Once I get there, that's the peak, and then it starts going down again. So it looks sort of like an M. We'll draw it that way. So let's make sure that everything from negative infinity, well, you know, negative infinity would be way out, off to the left forever until I get to -3, the graph's going up, which it is. It's got a derivative of 0 at -3, which it does. Then it starts to go down until I get to 0, and then the derivative is undefined. So that's why I have a little corner there. And again, you can just draw an open circle there if you'd rather. And then the graph goes up again, derivative of 0, graph goes down. So that graph works. Again, I don't know how high it is. I don't know if it goes through the origin. I don't know if everything's below the x-axis. It doesn't matter. But something like that would definitely work. All right. So anyway, that's kind of an idea of how we would graph these once we find these things. What I'm going to do next is I'm going to find everything that it tells me in 15. So when it talks about, oh, there's a positive derivative over this interval, negative derivative over that interval, I'm going to find all those things. So now we're going to jump into the calculus of it. All right. So here's what I'm going to do. I'm going to pull a couple problems out of the book. I didn't copy these because they're just written down problems. So I will just write them myself. The question says, for each function, find any critical values and any relative extrema. Okay, so this is problem 18. We'll write this down for this first one. Find critical values. Oops. And relative extrema. And remember, relative extrema means relative maximums and relative minimums. And I'm going to show you how we find this in this first problem. So there's a technique we typically use. We're going to use a sign chart. The function they give us, f of x, is x squared minus 6x plus 1. Okay, so remember critical values. How do we find critical values? Well, that was when the derivative equals 0 or undefined. All right, so let's do it. So we take the derivative, f prime of x, and I get 2x minus 6. Well, there's my derivative. So I'm going to set that equal to 0, and I add by 2, x equals 3. That's my only critical value. I'm not going to put the dots there. We'll just say CV to say it's a critical value. So I do have one critical value. Well, here's what we do. We do a little sign chart. So what I'm going to do is I'm going to put any critical values that I have there. That's the only one I have in this case. So it breaks the number line up into two pieces. Notice off to the left, this would be negative infinity to 3. And to the right, 3 to infinity. All right, but what I'm going to do is I'm going to test a number, any number in that interval. So let's say we'll test, well, 0's in here. That's a nice one to test. And over here, maybe 4. We can test 5, 10, 100. It doesn't matter. It just has to be any number between 3 and infinity. It can't be 3 because if we plug it into the derivative, we're going to get 0. But that's what we're going to do. We're going to plug it into the derivative. And so notice the derivative was just 2x minus 6. So when I plug that in there, f prime of x equals 2x minus 6. I'm usually just going to do this piece in my head, but I'll show you for this first time. F prime of 0, 2 times 0 minus 6, which is negative 6, which is less than 0. Again, I just like to say, oh, look, it's negative. So the derivative's negative. But f prime of 4 is 2 times 4. Well, that's a horrible 4. 2 times 4 minus 6, which is 8 minus 6, which is 2, which is greater than 0 or which is positive. And so if 4 is a number in that interval and it's positive, the derivative is positive in there, means every number in that interval will have a positive derivative, because the derivative can't change signs except at critical values. Now, what does this tell us though? Well, if the derivative is negative, it means the graph's decreasing. And if the derivative is positive, it means the function or the graph is increasing. And so we can just see from there, oh, if the graph's going down and then it goes up, there has to be a minimum at x equals 3. And so that's what I do. I answer the question by saying relative minimum and we may say it one of two ways. At x equals 3, sometimes they want to know what the point is. Well, the point, remember to get the y value, we plug that into the original function. So f of 3, which is going to be 3 squared minus 6 times 3 plus 1. Let's see, 9 minus 18 is negative 9 plus 1, negative 8. So the point when x is 3, y is negative 8, that's my relative minimum. And we'd already said that we had a critical value at x equals 3. And notice that function, which was f of x or y equals x squared minus 6x plus 1, we know that that graph's a parabola. And so we know it has a minimum. What we actually just found was the vertex. But the power of calculus is I can find any relative maximum or minimum regardless if it's a parabola or any other graph that I can take the derivative of. All right, so that's the idea. And if we were to graph it, you know, that's the relative minimum. We know it decreased till it got there and then it increased, your typical parabola. But that's the idea. So we'll jump in and this is all we're going to do. And we're going to find a little bit harder problems to do, of course, so that we can see how these work, but it'll just give us some more practice. That's the main idea. That's, in fact, the entire section. So we've seen the entire section. We're just going to practice it a little bit. Okay, so anyway, that's the idea. And let's go ahead and jump into the next problem. Our next problem, let's see, that was problem 18. I picked out problem 40 as our next problem. Jumping ahead a little bit. And they give us another function, f of x equals 3x squared plus 2x to the third. And now it'll help you out if you remember from algebra how to graph these things because you know what to expect. And maybe you know how to do that, maybe you don't. I will tell you what this graph looks like. And so what's happening with this graph, since it's a positive x cubed is the highest power, the graph's going to look something like this. So there may be a relative max and a relative min. Let's do it. Let's find out. All right. So we're going to use the calculus again to find out. And then we'll go from there. All right. So think about what the first step is to do. And hopefully you're thinking, oh, I need to take the derivative. And of course, that is absolutely true. So we take the derivative. We get 6x plus 6x squared. And then we set that equal to 0 to find any critical values. This is a polynomial, so it's never undefined, but it may be 0 somewhere. I like to often just put a 0 right there because then I can see if I look left, right, oh, the derivative is equal to 0. Well, to solve this, don't get rid of the 0. If you have x in more than one place, you're going to have to factor it out. I can factor out a 6x, and it leaves me with 1 plus x equals 0. And then I set each of those equal to 0. I get x is negative 1. And if I divide by 6, I'm not going to write it. I'm just going to say divide by 6. If I divide by 6, I get x equals 0. Remember, 0 divided by 6 is 0. So I get two critical values. So we'll say critical values, x equals 0, x equals 1. So that's the answer to the first piece. Now what this graph wants us to do, or what this problem wants us to do rather, is they want us to actually find the intervals where the graph's increasing or decreasing. Well, that's no big deal. We found that in the last problem. We just didn't specify it. All right, so let's see. So I've got this. Now, since I have two critical values, I'm going to put both of them on my line. And I often don't write the intervals, but think about what's happening. This is negative infinity to 0. This is 0 to 1. And this is 1 to infinity. So this time I have three intervals. I have to test a number in each of those intervals. So maybe -1. Now between 0 and 1, there's not a lot of choices. I'm going to put in a half or 0.5 if you'd rather do it as a decimal to do it in your calculator. And from 1 to infinity, I'll pick 2. Remember, I'm plugging those into the derivative because I want to find out if the graph's going up or down. And the derivative is what tells me that. It tells me if it's increasing or decreasing. Okay, so now notice, and here's what I'm doing. You can actually plug that -1 in here to the derivative and see if you get a positive or negative number. I like to actually plug it in here because all I have to do is worry about the signs. So for instance, if I plug -1 into 6x, I get -6. And then I plug, good heavens, we have to back up on this. If 1 plus x is 0, that doesn't mean x is 1, that means x is -1. I wrote that down wrong. We need to redo our signs. Okay, so we'll just put a -1 here. That won't be any big deal, but we need to change. Now here's what happened. Here's why I knew I did something wrong. And this is a good catch for us, because what I need to do, if I ever plug in a value and I get 0 when I plug it in, either I'm accidentally plugging it into the derivative, or I'm plugging in a critical value, which you can't do. You have to plug in numbers to the left or the right of critical values. So I should have done -1 and 0. So now I'll test -2, -0.5, and then +1. Okay, again, plugging them into the derivative. Now think about this, -2 times the 6 times -12. I don't care about the value, I just care that it's negative. And then 1 minus 2 is also negative. So what I'm doing is I'm taking this value and I'm plugging it in for that x value and that x value. The first one gave me a negative. The second one, the 1 minus 2, also gave me a negative. And I know a negative times a negative is a positive. So I know the derivative's positive. Why is that important? Because it tells me the function has to be going up. Notice we see that in the graph right here. Ooh, the graph looks good so far. If I plug in -0.5 to 6x, I get a negative. But if I plug it into 1 plus x, I get a +0.5. And a negative times a positive is a negative. So that's negative. Oh, the graph's going down. Yep, the graph was going down. And when I plug in 1, 6 times 1 is positive. 1 plus 1 is positive. Positive times a positive is a positive. There's my graph going up. Yep, graph's going up. So the original graph I drew was accurate as far as the depiction of when it's going up or down. So let's see. From -infinity, so this again, this was -infinity to -1, it's increasing. From -1 to 0, the graph was going down, it's decreasing. And then from 0 to infinity, the graph's increasing again. And so I could answer questions that way. When they said intervals of increasing or decreasing, we'd say, oh, it's increasing -infinity to -1 and 0 to infinity. I'm just going to put a comma there. Sometimes they put the little union symbol for or. Just do it however your author does it. And it's decreasing just between x is -1 and x equals 0. Remember, those are x values. When we talk about intervals, we always just list the x values. Okay, but again, notice if the graph goes up and then comes down, there has to be a max. And if it goes down and then up, there has to be a min. So there has to be a max here. There has to be a min here at 0. So we can list that. They do like to list it as ordered pairs. So they're going to say relative max. Now it's at -1, but we're going to list that as a point. And relative min, that was at 0. 0 is easy. We just, because remember, we're plugging back into the original function. So I'm going way up here to the original function to get my y value. Well, if I plug in 0, I just get 0. That's an easy one. So my relative min is 0, 0. But that was f of 0 was equal to 0. And we'll do f of -1. We'll calculate that. So it's 3 times -1 squared plus 2 times -1 cubed. Let's see, -1 squared is 1, so I get 3, but then -1 cubed is -1, so I get -2, which is +1. That's my y value. So that 1 was that one right there. It's f of -1. So I've got my relative max, my relative min, and that makes sense because we knew the graph looked like this. So it had a max, had a min, and we found out what they were. So we could graph from there because we know it's going up, then it hits a max, and we know where it hits the max, and then it goes down, it hits a min at 0, 0, and then it hits a max. So we could draw that real quickly. But I'm only going to have you, well, they may have you graph on the homework. In class, I only have you graph ones that you haven't gone through the steps to, just because we can break them up, and I think that's just too many steps altogether. Okay, but let's just do a couple more examples just to kind of get a hang of this. But notice we didn't do anything different other than actually list where it's increasing or decreasing. All right, the next problem just says find all relative extrema and sketch the graph. So they're not having us list increasing or decreasing, and they're not having us list critical values, but we have to find both of those in order to answer the question. So they give us capital F of x is the cubed root of x minus 1. I'm going to rewrite that as x minus 1 to the 1/3 power. Remember, roots are fractional exponents. Denominators are negative exponents. So the question just says find relative extrema. All right, so I take the derivative. So I go f prime of x, 1/3 x minus 1 to the -1 minus 1 is -2/3, and set it equal to 0. On these, one, I kind of like to write it back as in its radical form. But here's one thing to notice. If all of this stuff is being multiplied together and it has powers and everything else, the only way this can be 0 is if the stuff inside is equal to 0. I know immediately I can just say, oh, x minus 1 equals 0. X equals 1. That's my only critical value. And I'll show you why that's the case. Because here's what I would do if I was trying to actually solve this. And I'm going to go through the steps, and we'll go through them quickly because you're going to see, oh, I could have just taken that stuff on the inside. So here's literally what you would do. Multiply both sides by 3 to get rid of the fraction. Well, the 3 and the 1/3 cancel out. And so I get x minus 1 to the -2/3 is equal to 3 times 0 is still 0. And then usually what we do, the easy way to do this is we raise it to the reciprocal exponent, because when I multiply those exponents, it just gives me to the first power, which means I don't have to do anything. And so now on the left, I just get x minus 1, and it's to the first power if you want to think that way. We usually don't write that. But 0 to any power is just 0. Now the 2 on the bottom means the square root. Oh, the square root is 0, 0. The 3 on top means I cube it. Oh, 0 cubes just 0. Now, I will tell you, literally, it's undefined here. Because when I flip it over, because that negative exponent, 0 divided by 1 is 1 over 0. So it's really, when I flip this over, it actually comes to, instead of 0, it's 0 over 1. And the reason that is, and that's undefined. And I didn't care if it was 0 or undefined. I don't care if the top 0 or the bottom 0. Either way, it's going to be a critical value. So that's why I just set it there. But literally, let me show you what happened. When I've got this f prime of x equals 1/3, x minus 1 to the negative 2/3, we would rewrite that. Well, here, we'll put the equal 0. We would rewrite that this way. It's a fraction, 1's on top. On the bottom, I get 3 times the cubed root of x minus 1 squared. And so what we do, the derivative is equal to 0 when the top is equal to 0. Well, 1 never equals 0. That doesn't give us a critical value. So this is when f prime of x, oops, capital F prime, when f prime of x equals 0. Never equals 0 because the top doesn't equal 0. When f prime of x is undefined, that's when the bottom is 0. And so if I say, oh, this 3 times the cubed root of x minus 1 squared equals 0. And now I do what I did before. In this case, I'd divide by 3, then I'd cube it, then I'd take the square root, and eventually I get down to x minus 1 equals 0. So it's just this little piece right here. So set that equal to 0, and you get x equals 1, just as we said before. It's critical value. It's not where the derivative is equal to 0, but it is where it's undefined. Okay, so let's go from there. And so what we're going to do, and I'll show you what this graph looks like after we drew it. So at x equals 1, we have a critical value. So let's do this. We'll put our 1 there. I'm going to test, well, interval-wise, let's see. We go negative infinity to 1 and 1 to infinity. I'm going to test, let's say, 0 and 2 into the derivative. And then I'm going to see what the function itself does. Well, I've got the function, I've got the derivative written right here. Let's just do it there. If I plug in 0 for x, on the bottom I get negative 1 squared, which is 1. So it's positive. And then I take the cubed root, it's still positive. I multiply by 3, it's still positive. And then the top's 1, which is positive. 1 divided by a positive number is positive, so the graph's going up. If I plug in 2 there, 2 minus 1 is positive 1. I squared it, it's still positive. Everything on the bottom keeps it positive. Positive over positive is still positive. The graph's still going up. Wait a second, the graph goes up and then it keeps going up. That's not a maximum because it kept going up. It's not a minimum because it never went down. Doesn't have any relative extrema. No relative extrema. Because notice it went from increasing and kept increasing. You think about what you're going to have. You're going to have a maximum if it increases and then decreases. So if you go increase and then decrease, you have a relative max. If you go decrease and then increase, you have a relative min. And don't memorize, think about what's happening. Increase and then decrease. Oh yeah, that's a max. Decrease and then increase. Oh yeah, that's a min. So don't just try to memorize a billion things. Try to understand a billion things. The more you understand, the less you have to memorize. Okay, so this doesn't have any relative extreme at all. I'll show you what this graph looks like, and you may have remembered this graph from an algebra class, but let's look at it. We had the cubed root of x minus 1. looks like this. Cubed root x minus 1. If you remember that 1, that minus 1 moves the graph over to the right one. A cubed root graph, we'll draw it in blue, looks like, I don't know where that piece came from. Looks like this to the right, but it looks like this to the left. It looks like a sideways, the top of a sideways parabola to the right, but the bottom of a sideways parabola to the left. And what's happening right here at 1, that's my tangent line. And the slope of the tangent line there is undefined. That's exactly what we found out when we did it algebraically. It's a vertical line, slope's undefined. But notice the graph's going up over here and it's still going up over there. That's why it doesn't have a relative max or min, because there's no little circle I can draw, no interval in here where it's at a highest point or it's at a lowest point. It keeps going up, up, up. Every value on here, if you look left to right, the point to the right is going to be higher than the point to the left. Okay, so that's that one. I wanted to show you one that didn't have any relative max or min, no relative extrema, so that you know that can happen. So if you go increasing to increasing or decreasing to decreasing, there's no relative extrema. You could probably write that down here. So increasing to increasing or decreasing to decreasing. No relative extrema. And again, don't memorize that. Think about why that's the case. So that's the abbreviation of relative. I didn't want you to think that was an exclamation point. Okay, so I've got one last problem in here. It's another f of x problem. It's problem 56. Capital F of x equals, and this time it's a fraction. The numerator is 5, the bottom is x squared plus 1. And there's a couple things here I want to explain to you. Okay, again, it just says find all relative extrema. Find all relative extrema. So what do we do? Yep, take the derivative, set it equal to 0. Well, this time I'm going to use the quotient rule. And remember the quotient rule, low d high minus high d low, square the bottom and away we go. That's the easiest way to do it. For me, as far as how it's going to simplify and algebraically we're going to do it, you could do other things there to take the derivative. I would not recommend it. So I'm going to go low d high. Well, the derivative of 5 is just 0. So this whole thing, that's gone. That whole thing's just 0. Minus high d low. Square the bottom and away we go. So it just simplifies to negative 10x over x squared plus 1 squared. Now, we're going to set that equal to 0. Remember, with a fraction, when the top is 0, that's when the fraction's equal to 0. When the bottom is 0, that's when the fraction's undefined. But they both give you critical values. At least they both potentially give you critical values, and you'll see why I say potentially in just a sec. So over here, I'm just going to divide by negative 10. We'll do that in blue so we see the original problem, and negative 10 divided by, or 0 divided by negative 10 is just 0. So I have a critical value at 0. Over here, I'd take the square root, and I'd usually say plus or minus, but the square root of 0 is 0. Positive and negative 0 are the same number. And so that gives me x squared plus 1. Square root's gone, equals 0. Subtract 1, x squared equals negative 1. Again, take the square root, say plus or minus this time, but negative 1 is a complex number. The square root, rather. So this x plus 1, I mean x is positive or negative I. It's imaginary. Imaginary numbers are not critical values. We'll just say CVs. So that doesn't give us a critical value. The only critical value I have over here is 0. So I have one of them. So let's go over here and we'll do our chart. So it's 0. We'll look to the left, -1, look to the right, 1. Again, we plug those into the derivative. Don't forget where we plug those in to see what's happening to the original function. And the derivative, well, here was the derivative right here. Let's circle that in blue. There's my derivative. There's f prime of x. Now, here's the good thing about the quotient rule. The denominator is squared, so it's always positive. Well, we know for sure it's always non-negative. It might be 0, but we just showed that it couldn't be 0. Plus, if it was 0, we wouldn't be testing that anyway. Any test value we're going to plug in is always going to make the denominator positive. So I really only have to look at the top. And if I plug in -1, -10 times -1 is +10. So the derivative is positive. So the graph is increasing. And if I plug in 1, -10 times 1 is -10. So the graph is decreasing. So there has to be a max at 0. And again, just picture the graph. We know the graph goes up, then it comes down. Oh, there has to be a max. So then I can go answer this. I'm going to say, oh, it's got a relative max at 0. And when I plug 0 into the original function, I get 5 over 0 plus 1. Well, that's just 5 over 1. That's 5. We'll write that down. That should be easy enough. So relative maximum, we know it's at 0, comma. Well, the next number, that's going to be f of 0, which is, what do we say, 5 over 0 squared plus 1, which is 5 over 1, or 5. That's my y value. If we wanted to say the graph was increasing, remember, it's going up from -infinity to 0. And it's decreasing from 0 to infinity. We could have said that. They didn't ask us on this question, but we definitely know how to answer that. And it's looking kind of weird. We're saying, what in the world does this graph look like? Well, I'll show you what it looks like. The relative maximum is 0, 5. So that's as high as it gets. But there's no minimum. The reason there's no relative minimum is the graph, there's a horizontal asymptote at 0. The graph is coming up this way until it gets there. And then it comes back down over here, back down towards the x-axis. That's my graph. And notice it's 5 over something squared, or x squared plus 1. The x squared plus 1 on the bottom is always positive. The top clearly is 5. It's always positive. So this graph can never be negative. So that's what the graph looks like. Notice it's increasing over here, -to 0, decreasing from 0 to infinity. All right, that is the end of that section. Hopefully some of this stuff made sense. Work through it, do some problems, look back over at the video if you need to. But this takes some practice. This is the first chapter that's really applying the different things that we've done. And this first section, I think, is probably the toughest section because it's the most new stuff. We will build from it in the other section. There's a lot going on in this section, so it is going to take some work. So anyway, work on that, do the best you can, and we'll answer questions about it in the live session. All right, best of luck to you, and practice.